Good morning, everyone. My name is Seongju Lee, and I'm a graduate student at Hanyang University in South Korea. And my advisor is Professor Simon Song. Today, I'll be presenting our work titled Magnetic Resonance Velocimetry for Multiphase Flow Mapping, Probabilistic Identification of Time-Averaged Bubble Withdraws. Dishwashers are now a common appliance in everyday life. Dishwashers contain a sump at the bottom with several filters. The flow characteristics inside the sump is closely related to the filtration performance. And understanding the flow path of air bubbles is also crucial for protecting the pump located directly downstream. However, the sump has a highly complex internal flow path, and the flow within it is fast-moving and multiphase, making optical visualization extremely challenging. However, magnetic resonance velocimetry, or MRV, uses a clinical MRI scanner and can measure time-resolved 3D 3C velocity fields in a completely non-invasive way. Thanks to this capability, MRV has gained considerable attention in engineering research. Recent work has applied MRV to various flow investigations, including measurement of turbulent kinetic energy. However, most of these studies have focused on single-phase flows. So the reason is as follows. MRI acquires its signal from hydrogen nuclei. So regions with very few hydrogen atoms, such as air bubbles, produce little or no signal. As a result, we see signal loss in the MR magnitude images, and in the velocity data, these regions often appear as noise-like random velocity distributions. So let's look at one recent multiphase flow study conducted using MRI. In this work, researchers examined air bubbles rising in a stationary fluid. And by using a fast imaging sequence called EPI, they captured snapshot images of buoyancy-driven bubbles and estimated their rising velocities. However, this study was still limited to relatively simple conditions involving slow-moving bubbles. So the aim of this study is to identify time-averaged bubble withdraws in dishwasher flow using MRV. To achieve this, we have to understand MR signal loss and velocity noise patterns due to bubbles. And then we have to determine the parameter that identifies bubbles in multiphase flow. And then we can visualize multiphase flow inside the dishwasher. The MRV experiment was carried out using a scaled model of the dishwasher sump. At the bottom of the dishwasher, there is a tub, and beneath it are 3 filters followed by the sump. All components were fabricated using a 3D printer, and the entire model was reduced to half of the real size to fit inside the MRI ball. We tested 2 operating conditions, which were distinguished by the initial water level, one with a higher level and the other one with a lower level. This is the MRV setup used to measure the dishwasher flow. The flow loop consists of 2 pumps, 2 flow meters, and a reservoir. And the 3D printed model was placed inside a 3T human MRI at KBSI Ochang. We acquired 3D velocity data over a 280 by 280 by 120 millimeter field of view at 0.5 millimeter isotropic resolution. The total acquisition time was roughly 1.5 hours per case. This slide explains how the bubble index is calculated. The method is based on the assumption that bubble regions in MRV exhibits a random velocity distribution due to phase noise from low proton density. We first obtain the average speed from a confirmed bubble region and use this as the reference bubble velocity. For each voxel, we then define a computing ROI around it and compare the speeds within this ROI to the bubble velocity. And then the difference is normalized using the top 5% of speeds in the ROI so that the index ranges from 0 to 1. And values above 1 are clipped. So if the velocity magnitude within the computing ROI follows a noise-like distribution whose mean is close to the bubble velocity, then the bubble index approaches 0. Now, let's look at the results. This video shows the 3D velocity field together with the bubble index. In the velocity field, the color contour represents the outer plane velocity, while the arrows indicate the in-plane velocity components. The gray mask shows the bubble regions identified by the bubble index. On the bottom, you can see the bubble index map. Regions that are likely to contain bubbles appears dark, with values close to 0. Here, we show the bubble index on representative cross-sections. Among the 3 filters in the sump, the cylindrical mesh filter has a cap-like structure on top, where bubbles tend to get trapped easily. In the top view slice, the sump outlet is positioned roughly at the 7 o'clock direction, and on the opposite side, we observe a region with a low bubble index, indicating the presence of the bubbles. And then when we compare the 2 operating conditions, we can see that the bubble-rich region becomes noticeably larger when the initial water level is lower. Then we compare the volume of bubble-rich regions between the 2 cases. When we apply a bubble index threshold of 0.7, the real scale volume in case 1 is about 55 cc, whereas in case 2, it increases to roughly 86 cc. This means that a lower initial water level promotes stronger air entertainment at the sump, resulting in a larger bubble-rich region, about 58%. To summarize, we developed the bubble index to quantify bubble-induced velocity randomness. This helps address the challenges of applying MRV to rapidly evolving bubbly flows. Using this metric, we compared bubble-rich regions under different operating conditions. Future work will aim to separate bubble-induced randomness from noise-like patterns caused by acceleration or turbulence. Thank you.